Hi, welcome to Precalculus. Today's topic is identifying symmetries of graphs given their polar equations. You have seen this topic before in college algebra when you looked at equations and you wanted to figure out if the graph is symmetric with respect to x-axis, y-axis, or the origin. We are going to look at essentially the same kind of question, but in the context of polar equations. Let me try to motivate this topic among all the topics we have looked at in this semester. This is the most substantial one. So let me tell a few stories here and there. Hopefully it will motivate you to study the topic in your area of interest. Okay, here is a picture of Miss Crawford and its mirror image. Let me tell you a story about this one. I was in a barber shop many years ago, and there was a picture on the cover of a magazine, and I looked inside the magazine, and there was another picture of the Miss Crawford, but it looked oddly different. After going back and forth between the two pictures, of course for scientific curiosity only, I noticed that one of them has a beauty spot on the left and the other one is on the right. So obviously whoever arranged the page and made a mistake of flipping the picture and putting it in the wrong direction. So at that point the question comes up, if you don't know Miss Crawford, can you tell which one of these two pictures is the correct one and which one is the result of an error? Well, there is a version of this question that's actually so fundamental that led to a Nobel Prize sometime in the 50s. The question is, does the universe have a beauty spot that shows up only on one side? Oh, what does that mean? Suppose we have a gigantic mirror, we can put it in front of the whole universe and take a video of the universe and take a video of the universe in that humongous mirror. If you are looking at these two mirrors, at these two videos, can you tell which one of them is the real universe and which one of them is a reflection in that mirror? So the topic is extremely deep, and we wouldn't have, of course, time to look at that. It's just that we want to mention that the issue of symmetry, of course, is very important in art, in architecture, in biology, in chemistry, physics, crystallography, mathematics, and pretty much all the areas of science out there. So you might come across this issue yourself. You're used to your own face, the way it appears in the mirror, but that's of course the reflected image of you. It's not truly you. To notice the difference, if you stand with a family member in front of a mirror and look at their image in the mirror, you might be surprised how different that image looks from the perception that you have about the person. To experiment that on yourself, perhaps you have to go to a fitting room of a department store where they have double mirrors, and when you look at the double mirrors you see three images of yourself. Two of them are regular reflected images, and the third one is how you appear to other people, and that third image looks quite different from what you are accustomed to. With the phones, and you take many selfies and gradually you get used to that other image of yourself, which is corrected for this issue, but still there's room for surprise. Let me take you through a few pictures here so that we see what the issue is. So here issue of symmetry with respect to lines, something that you have seen in college algebra or in pre-calculus 1. So symmetry with respect to x-axis, y-axis, and origin was studied over there. And symmetry with respect to origin, a little bit more complicated. But here is the issue of reflecting an image with respect to a point and getting another image. And sometimes when an image is given, you want to figure out if there's a point of symmetry in it or not. Here is a website with extensive listing of symmetries in chemistry. So as you see, there's a long list of symmetries listed. Among each of them are subgroups. So for example, this is supposed to be twistane, a kind of a chemical compound. And if you rotate it with respect to any of these three axes, you see that it coincides back on itself. And that's the notion of symmetry. Symmetry, it means, we say an object is symmetric with respect to an action if the original is indistinguishable from the final result. So for example, if you have a circle and rotate it by some degrees, still that same old circle. So you say a circle is symmetric with respect to any rotation. How about a square? Well, square, if you rotate it by 90 degrees, it becomes indistinguishable from what it was. So you say a square is symmetric with respect to a 90-degree rotation. How about a hexagon? A hexagon is symmetric with respect to a 60-degree rotation, and so on. So the issue of symmetry is quite significant in many different areas of science. Let me give you an example from botany. In preparation for this lecture, I became curious. Is there a flower that is symmetric with respect to its pole, but not with respect to x or y axis? So I posted this question, and the question got 2,000 reviews. Nobody had the correct answer, but following the leads, we could find finally a flower. Here is a result of our search. Here's a special type of flower that doesn't have symmetry with respect to x or y axis, but has symmetry with respect to its pole, or with respect to its origin, the central point of the picture. One trivia topic I can mention here is that I tried to do this search on ChatGPT and it couldn't find it. So amazingly enough, it's not a well-known flower. Okay, with respect to biology, we see the issue of symmetry quite often. Human body from the outside, it looks somewhat symmetric, but if you look deeper, of course, it is not symmetric. Most of us are right-handed. Our heart is usually, almost always, is on the left, and so on. You might wonder, is it possible for a human being to be a mirror image of ordinary human being, meaning the heart to be on the right side, and so on, all the internal organs to be arranged in the opposite side? Is it possible? Well, it does happen, but it's extremely rare. It's called situs inversus. So it's a topic of research in biology. Why does the universe choose one style as opposed to the other one? In physics, as I mentioned, the issue led to a Nobel Prize many years ago. And if you're interested in any of these areas, you might want to go ahead and dig deeper and find out. So what is the topic that we are going to look at today? So starting back to our standard mathematics, we are going to look at symmetry with respect to polar axis. That's our old x-axis. With respect to line theta equal to pi over 2, well, that's just the y-axis. or with respect to the pole, that's just same as our old origin. So these are the same symmetries as the ones we have seen in college algebra, is just expressed in a different style. So let me go ahead and explain the criterion. So again, what is meant by symmetry? If you have an object and take that object and perform certain action on it, move it in a certain way, and the final result looks exactly like the original one, then you say that object has symmetry with respect to that action. So what does it mean to say an object is symmetric with respect to the polar axis? What does this mean? Sorry. So here we draw the coordinate system. This is, of course, the x-axis is called the polar axis. If an object is such that it has these 2 points in it, we say it is symmetric with respect to this polar axis. Meaning what? Meaning if I flip this, like let's call this thing point A and this one point B. If I rotate this picture around the x-axis, then A comes on top of B and B goes on top of A, and final picture looks like what we had at the very beginning. So it is symmetric with respect to the polar axis. If we have a shape that is like this, we say that shape is symmetric with respect to polar axis. In college algebra, well, this one has positive, A has a positive y coordinate, B has a negative y coordinate, and we say if you change y to minus y in the equation and the equation doesn't change, then you say it is symmetric with respect to x-axis. Well, how do we do that if everything is expressed in a polar language? How can we tell something is symmetric with respect to this axis? Well, we say this one is the point r and theta. Well, this is r, of course, and this is theta. How about the other one? The other one is the point, again, its r is just r, but one way to express the point B is to say, well, this is minus theta. If the equation is such that I replace r and theta with r and minus theta, and what I get is the equation I had to begin with, well, I say it is symmetric with respect to x-axis. That is, if r and theta is satisfying the equation, then r and minus theta is also going to satisfy. Now, in polar coordinate, we have a new twist to the story due to the fact that each point has infinitely many representations, and we have to check all of them, which makes the problem slightly more complicated. But we are just going to limit ourselves to this, to a few of these representations. For example, this point B, I could have gone to this line. That line is at the angle pi minus theta. If this is theta, that's going to be pi minus theta. And on that axis, I could have backed out by minus r. To get to B, you have two options. Take theta and convert it to negative theta, that brings you down. Or take theta, convert it to pi minus theta, and then on that line, go back to minus r. So we have this other alternative expression for this point, which is minus r and pi minus theta. In fact, we have, again, as I said, infinitely many representation of each point in the polar coordinate. We have to look at all of them, but we are going to limit ourselves to just these. How about symmetry with respect to y-axis? Symmetry with respect to y-axis in college algebra job, you say if you change x to minus x and the equation doesn't change, it's symmetric with respect to y-axis. For example, graph of y equal to x squared, you change x to minus x, and minus x squared is same as x squared, and you say your graph is symmetric with respect to y-axis. How about here? Well, if I have, again, let's look at the point A. Suppose that and B, both of them are on the same graph. If that is so, then it is symmetric with respect to y-axis, which is theta equal to pi over 2. But how is that in polar? So as usual, we say that this one has coordinate r and theta. Easiest way to go to point B is to say, okay, draw this, go on this axis. The axis is at the angle pi minus theta. Go by distance r on that axis. So r and pi minus theta brings us to point B. Well, what is the other option? Other option is to come down to this direction. Imagine point C down here. Come to this axis, which is at the angle of minus theta, and then in this axis go back out by r, meaning go to the other side by minus r. So it becomes minus r and minus theta. That is another representation of point B. So if I have an equation with r and theta in it, if I take theta and replace it by pi minus theta, and I get the same equation that I had already, I say, well, I'm already done. It is symmetric with respect to y-axis. Or if I change theta to minus theta as well as r to minus r, and the equation doesn't change, then I say I have an equation whose graph is symmetric with respect to the y-axis with respect to theta equal to pi over 2. Okay, these are the two most immediate checks we can do, and there are, as I said, infinitely many other tests we need to do to be complete. But just to keep the problem doable and short for now, we just do these two tests. So we take r and theta, replace it by r and theta, pi minus theta. If it doesn't change, we say, okay, we have discovered symmetry with respect to theta equal to pi over 2. Round 2, we change r and theta to minus r and minus theta. If the equation doesn't change, again, we are legitimate in saying that it is symmetric with respect to y-axis. However, if our checks doesn't work, that is, the equation is different after we have changed r and theta to either of these, we leave the question open and we say our test is inconclusive because we haven't checked the other representations of point B. So that's the complication in polar that wasn't there in the Cartesian. In Cartesian, every point has just one representation and your checking is a lot simpler. Here, the issue is more complicated. And the third one is symmetry with respect to origin. That's the story I was trying to follow with respect to that flower over there. So I was looking for a flower that doesn't have this symmetry, doesn't have that symmetry, but only has this one. Overwhelming majority of flowers have plenty of axes of symmetry. Everything, the petals and the arrangement of the petals are symmetric, but I didn't want that. I just want to have point symmetry, which means what? If I have a point A here, again, point A is at the location r theta. I go to the origin, go equal distance to the other side. I come to the point B, which has coordinates r. And what's the theta now? This was theta, and that one now we have to go all around, which is pi plus theta. So if I change the theta of an equation to pi plus theta, I'm back to the same old equation. I say the graph of that equation is symmetric with respect to the origin. Well, is there another way of coming to B? Yes. Just consider this axis. On this axis, which is at the angle of theta, if I go back up, so if my angle is theta, but I go choose the point with location minus r on that axis, that would be same as B. So if I change r and theta to minus r and theta, and the equation doesn't change, I say that the graph of that equation is going to be symmetric with respect to the origin. Okay, these are the type of problems that you're going to face in this section. Here's a simple version of it. Two familiar polar equations are given to us, and we want to check if they are symmetric with respect to polar axis or y-axis or x-axis and so on. So this is of course x-axis, this is the y-axis, pole means the origin. Is this symmetric with respect to x-axis, y-axis, or the origin? Okay, to answer these questions we can do it one of two ways. If the curve is something that is familiar to us, then we can go through our knowledge of those curves and answer what type of symmetry it has. If the curve is not familiar to us, then we can apply the test to it. So for example, you remember this is a limacon. It's a dimpled limacon, and the sign indicates that it's in the vertical direction. Therefore, it's going to be symmetric with respect to the y-axis. So our first inclination is that that would be the case here. Limacons are not, with the sign, they are not symmetric with respect to x-axis or the polar axis, and they are not symmetric with respect to origin or the pole either. And for the second curve, r squared equal to 4 cosine of 2 theta. You remember that was a picture of a ribbon or lemniscate. Lemniscates with cosine were horizontal. They were symmetric with respect to the x-axis or the polar axis, so that would be checked here. And they will be also symmetric with respect to the vertical or y-axis, line theta equal to pi over 2, and they are also symmetric with respect to the pole or with respect to the origin. So all three of these things. So again, if you remember, this had a picture something like this. And this one had a picture something like this. This was a dimpled limacon. So the axis of this one was, this is the axis of symmetry of this one. This one is symmetric. Well, y-axis, x-axis, and when both of them are there, the origin is always there as well. Okay, so if the picture is familiar, you can rely on memory and do that. But what if we wanted to actually apply these tests? So let's remind ourselves, this was the case of symmetry with respect to the polar axis. So we check to see if the curve doesn't change by making such changes. This one was symmetric with respect to line theta equal to pi over 2, which is the y-axis, and for this case we check with respect to changes of r and theta to either of these two. And finally, this was symmetry respect, so this was for the y-axis, or theta equal to pi over 2. This one with respect to x-axis, or also called the polar axis. And this one with respect to the pole, which is just same as the origin. So for this one we change r and theta to now let's go ahead do these tests. So okay, so we can perform the test, the three tests that are mentioned here, and let me write it down and perform them. In this space here. So let's take the first one. R is equal to 5 plus R is equal to 5 plus 4 sine of theta. So we have, let's make a list here with respect to x-axis, or the polar axis. That would be changing r and theta to r and minus theta, or minus r and pi minus theta. With respect to y-axis, or theta equal to pi over 2, that would be changing to r and pi minus theta, or minus r and minus theta. And with respect to the origin, which is also referred as the pole, this is going to be changing r and theta to minus r and theta, and r and pi plus theta. So checking with respect to x, or the polar axis. So I change r to r, theta to minus theta. Now, is this same as what I had originally? Well, let's simplify. Is it the same? By negative angle identities, for r is equal to 5 minus 4 sine of theta, and these are not the same, so this test fails. If you try to the other one, minus r is equal to 5 plus 4 sine of pi minus theta. How about that one? Well, this is minus r is equal to 5 plus sine of pi minus theta is same as sine of theta, so it becomes 4 sine of theta. Again, this is not the same. This is not the same as the original. This is not the same as the original. So our test does not support that the x-axis is axis of symmetry. So in that case, we just leave this thing and move on to the next one. How about the y-axis? Well, for the y-axis, I have the original is 5 plus 4 sine of theta. let's we are going to perform these operations. So I would write r is equal to 5 plus 4 sine of pi minus theta. Well, that is sine of pi minus theta is sine of theta. So we made a change, and the equation did not change. That means we do have symmetry with respect to y-axis, or the line theta is equal to pi over 2. So that one verifies. How about with respect to the origin? So in this case, I change r to minus r. So again, I start with the equation that is given to me. I change r to minus r. Then I ask myself, is this same as what I had at the beginning? Obviously not. This is r, this is minus r, and this one does not pass the test. If I change it to r and pi plus theta, I will have r is equal to 5 plus 4 sine of pi plus theta. If I simplify that, it becomes 5 sine of pi plus theta. You can work it out that it's going to be minus sine of theta. Again, this equation is not what we had at the beginning, and therefore this test also fails. So therefore, with the test that we have at our disposal, we cannot say that this picture is symmetric with respect to the pole. So that one is not going to be chosen. How about Leibniz gate? Leibniz gate has symmetry with respect to x-axis, y-axis, and the origin all around. Let's see. R squared is equal to 4 cosine of 2 theta. Let's do test number 1, changing r theta to minus theta. So we change theta to minus theta. So it becomes 4 cosine of 2 times minus theta. Well, you remember negative angle identity. Cosine of theta or minus theta are equal to each other. So this one already passed our test. We don't need to go do another test. So these are the same. And so we have symmetry with respect to polar axis. That's why we checked it. How about with respect to line pi over 2? So I'll have, again, I start with the equation that I'm given. Then I change my theta. So I change my theta to pi minus theta. So I'll change it, my theta. So I write r squared is equal to 4 cosine of 2 pi minus theta. So this was one of the options that we had. Change theta to pi minus theta. So what happens? So I'll have 4 cosine of 2 pi minus 2 theta. You can expand that and see that that is actually same as cosine of 2 theta. Cosine of 2 pi minus 2 theta is same as cosine of 2 theta. These are the same. So we have symmetry with respect to y-axis. Finally, symmetry with respect to, so this meant symmetric with respect to x-axis or the polar axis. This one means symmetric with respect to theta equal to pi over 2, which is the same as y-axis. And finally, again, we start with the given equation, and then we change r2 minus r, for example, and that would be the fastest. So I will have minus r. I change r to minus r, leave everything alone, and then I ask myself, is the new equation same as the old equation? Well, of course it is, because minus squared is just positive. At the end, when I simplify, I go back to whatever I had at the beginning. So that is symmetric, symmetric with respect to the pole, all with respect to the origin. So again, you have two ways of answering this. If your curves are familiar to you, well, you have the picture in front of you and you can easily make the choice. A more advanced way of this is to apply the three transformations that we talked about and see if the equation does not change with respect to the changes you made, then you have the symmetry. If not, we cannot be sure unless we do a very complete check. Okay, so I hope this topic interests you in some application of mathematics. Again, I want to mention that if you are interested in chemistry, excuse me, okay, if you are interested in chemistry, let me know, and we take a look at those. Okay, there is a bit more about the issue of symmetry on my website. In that particular link to that chemical compound website is listed there. Again, you can go through a large number of list of molecules with various kind of symmetry. Take a look at that, play with this thing, and see how this issue comes up in that topic. Until next time, good luck and God bless.